Thank you very much. I'd like to thank Chris and the OOCC for the invitation to talk about some of my research. I started a few years ago with the COC. There's lots of different acronyms at the Table Owl Commission, and they kind of wanted to see this move forward, but they immediately saw as we started inoculating different varieties that it went across the board, and they've been encouraging the olive oil group, and with the help of Adam, we've been able to get the support and progress made to fund joint projects. And so this is one of the first projects that's been jointly funded by both the whole, I guess you call it the entire olive industry of California. So I'm a plant pathologist, and that means basically I'm an applied microbiologist. I do things in the lab, and I try to do things in the field and relate that information back to the grower and the producer and how to manage problems. So this particular project's on the epidemiology, which means how the disease spreads, and then ultimately the management. How do we control something and bring it down to where we can produce our crop with minimal impact from what we consider a considerable threat to the industry, the Pseudomonas sevastanoid, Pathovar sevastanoid. This is the bacterium that causes olive knot. I'm in the plant pathology and microbiology department at UC Riverside. I was 10 years at Davis. I transferred to Riverside, but I maintain labs in Davis, Riverside, and at Kearney, where they're all staffed by technical staff called SRA, Staff Research Associates. So I was one of the logical people to work on a project like this, and I covered the entire state of California. So what I want to quickly do is just give you a quick overview of the epidemiology of olive knot, talk about some of our why how it causes disease. Let's be very quick. Review, and talk about some of the things that we did to come up with to help manage bacterial diseases like olive knot, and then coming up with new treatments to combat and develop. You can't just live on one material like copper. And so we're trying to get other materials, and many of you are familiar with agricultural production and pest management, and that's basically introducing different modes of action in rotation to prevent selection of resistance. So some of the information we have is going to be based on how we identify it, how we can know what we're working with, and then how the goal is to actually tell growers exactly how to manage this disease and how to prevent it from getting worse. The symptoms of olive knot are very clear. You get a gall. A knot is the common name for a gall. And these bacteria produce these phytohormones that can cause the plant a rapid multiplication of cells within the host. So it is stimulating, the bacterium stimulating the host to produce these galls or knots. And what these things are like houses. They're like houses for where the bacteria reside. And so they live in these galls, and when it rains out, they ooze out and produce the bacteria from that internal tissue where they're living inside that gall. We've been able to identify these things. They have, talk about UV light and looking at quality. When you grow these bacteria, they produce pigments that are also UV fluorescent, and Pseudomonas species are known for that, and if you put them under long-wave UV, you can actually see them fluoresce. This bacterium is omnipresent, and what we've been able to show is that it exists on the surface of plants, also at very low levels, but it's in concentrated form in those galls. We've been able to verify not just by culturally, but we developed and tested specific amplification. This is a molecular tool, sort of like a pregnancy test. It's either plus you have it, plus you don't. And when we test these galls, we can test if there's the bacterium is present inside there. What we've been able to show is that economically, reviewing the literature, this occurs in all of the olive growing production areas of the world. Both olive oil varieties as well as table olives are susceptible to this disease. And the primary entry is through wounds or injuries. We'll show you some examples of how the disease can move in the plant, and we'll give you some examples. But As I pointed out, it's an epiphytic at first, but then forms these endophytic populations in those knots or galls. The infections basically, if you start out small, you can prune it, keep the tree viable and growing. But if you start getting excessive knots, it can be a rate-limiting disease on production. And we know people that have taken out fields because of this disease. So it is a threat to the industry, and we have to stay on top of it, and that's why we're working on this to try to prevent it from ever becoming a limiting factor for producing olives and olive oil in California. One of the reasons why this thing has become so important is because of we've gone to high density, we've gone to mechanical methods of pruning, mechanical methods of harvesting, and that's what makes it so attractive. We can reduce our labor costs and we can mechanize that. But in doing so, we can create a lot of injuries. And so that's what we have to think about when we manage this. And that's how I got introduced just three years ago. How can we manage this disease? Knowing a little bit about the biology about this organism. Let's talk a little bit about the epidemiology. I already pointed out. These are the leaf scars. Olive leaves are evergreen, but they do drop their leaves at certain times of the year, especially in the spring. They're going to lose some leaves. Those little points of attachment for those leaves are going to fall off, and they can be immediately a source of entry for the bacterium into the plant. But the good news is we'll show you in a little bit, that they heal over, and they heal over very quickly. Cold injury, mechanical injury, these are the other major things. One of the things we can't control is cold. So as we go further north, it gets colder. And that's our historical perspective in California agriculture, but it can get cold in Fresno, and it can get cold down south. And cold injury can be an entry point for the bacteria. Mechanical injury, as I just pointed out, pruning, harvesting, even hail damage can be a big factor where you get injury, and then it rains like a thunderstorm, and even though it's very localized, you can still get significant damage into your fields. So high density planting with mechanized harvesting, pruning operations with these types of automated prunings and automated harvesters can create injury and can cause increased potential for this disease. So, time of infection, we see it mainly as a late fall, winter, and spring disease. The spring is with the leaf drop, the winter is with the cold, and the late fall, again, with the mechanical harvesting being a big factor in causing scraping injuries, which are ideal. Knot development is most people don't know this on the timeline. If you get an injury, you get an infection, you won't see that knot for about 3 to 6 months, depending on the time of growth or when it was infected. There's certain times of the year the trees are growing very rapidly, the knots will form quicker. In certain times of the year, the trees are growing very slowly, and so it takes months to see those knots. You just don't get an injury, and all of a sudden next day you see a knot developing. It usually is coincided with plant growth. Remember now, the bacterium is stimulating the host with these phytohormones that are causing the multiplication of cells and enlargement of cells. So that takes time. And so the events that give you the knots are usually, on average, 4 to 5 months before you actually see the symptoms. So environmental conditions, not so much temperature. The bacterium grows over a wide range. The temperatures are for the injury. Wetness is critical, though, because the rainfall precipitation is a vector mechanism of moving the bacterium from its house, that knot, to the injury sites that have occurred. Okay, so we've done some studies. We looked at olive knots, and when you look at these knots, all the knots that we've collected, they contain viable inoculum. If we rehydrate the olive knots, basically 1 hour, if we just soak them in water for 1 hour, they'll start producing the bacteria oozing out. In 18 to 24 hours, nearly 100% of the knots that we collect will produce inoculum. So it's a good rainstorm, and on the surface of those knots, there's lots of bacteria. That's the message. How much inoculant do we need? Like most bacterial diseases, we work on walnut blight, we work on fire blight, we work on all kinds of bacterial diseases. And it's a basic concept that you need a lot of bacteria. These are a logarithmic scale here, but as it increases population of bacteria, you get greater and greater chance of the population invading the injury causing knots. So if you have low population, so if you reduce the total number of knots in your field and keep it low, the chances of this bacterium spreading as it gets diluted by the rainfall is minimal. You won't have as much problem. But if you get a lot of knots and there's rainfall, then there's more uniform populations and higher levels. It can cause the disease more readily on those injuries. The other thing that we've been working on is wound healing and leaf scars. This is what I was alluding to earlier. Fortunately, the plants can heal up. Not all these injuries are susceptible for months at a time. And so what we did is do a quick study here, just looking at the duration of susceptibility. We inoculate injury, we go out to the field, we make injuries, some lateral injuries or pull off leaves, and where the leaf scar is, we inoculate it with that bacterium. And then we look at how long, so we do it in different time periods. In this particular graph, we have 0 days. So right when we created the injury, nearly 100% become infected. When you wait 10 days, you can see it drops off for leaf scars very quickly. So over here, in our greenhouse and field studies, leaf scars, basically in 10 days after you cause the injury, they heal over and they're no longer an entry point for the bacteria. So if you're going through a peak season of leaf drop and you're going to go into a rain, you have to have protection during that time period. If it's after 10 or 14 days, you don't need any more protection. If your leaf drop is, say, mid-April, end of April, and now you're into the middle of May, you won't need to control if there's a rain forecast because those leaf scars have healed over. So you have to realize those types of injuries. The other thing we did is these lateral wounds, and this is like related to the mechanized aspect of harvest, for example, where you get scraping injuries. And it's a little bit longer. In the greenhouse, it was about 14 days, and in the field, 10 to 20 days, depending on the growth stage of the plant, to get greater than 90% reduction. So the age of the injury is critical, and wound healing by the plant naturally happens. It'll dry out, and that wound will not be susceptible over, even if you have wetness and bacteria where it becomes resistant to the infection. The other thing I pointed out, we did studies at Davis. We planted, we have our own olive oil orchard there with Argentina as the variety, and we've done tests comparing overhead irrigation versus no irrigation, and we can see that the bars are basically the same here. So the wetness periods aren't interfering with wound healing. That's the good news. So if you get a rain and it's in the springtime, those wounds will heal probably very quickly within 10 days. If it's in the fall going into cold spell, that temperature slows down the response. It might take 20 days for that injury to heal over. The other thing we're looking at some of the slides here got a little bit changed, but some of the things we're looking at here is people pointed out to us that we can see different types of symptoms in the field. We have typical knots here in the lower left, where you see the typical gall, and then we have over here the systemic infection. And we've seen growers pointed out to us, we've been out to various plots in Northern California, and we see dieback symptoms of branches, and then we see this kind of galling on a wide kind of swollen area, not a typical localized, but just a whole stem. So we went back and looked at temperatures in 2014 and compared 2012, 2013 to 2013 to 2014. And basically we can see that when you get this is the lower temperature limits out of the CIMA station, the nearest CIMA station where we saw the injuries and this type of symptom development. So we made a correlation, basically, that when we see this temperature get down below 0 in centigrade, freezing temperatures for extended periods, here and here, then subsequent rains follow that. These are the worst kinds of situations for an olive situation where you can get what we think systemic infections are occurring. Up here, we didn't see any of those systemic type symptoms here. We did see some cold weather though, but the rain didn't come after. The rain was before, and we didn't see that. So we didn't see those types of symptoms. We took this to growth chambers. We did both manzanino and arbequina olives. We made the wounds. We put them in growth chambers, and we can get typical symptoms. Again, this takes a couple months to inoculate. You wait a couple months, and we can see the symptoms are typical. Now, when we took those plants and put them at low temperature chambers, exposed them to -5 centigrade, which is pretty cold, about 26 Fahrenheit, and then we just left them there for so many hours and took them out. We did see extensive defoliation, and then we saw where we inoculated, we got a gall, but then we also saw this swollen stem effect, and this was where basically we were able to re-isolate, so the bacterium left its house and moved up the xylem tissue into the other portions of that. So that systemic infection is a real thing. It's normally a localized infection, but we can get environmental conditions that can give us internal movement within the plant. So that's like the worst case scenario for this particular disease. As far as management goes, we can shift gears and talk about how to maintain the tree's vigor, reduce tree stress, reduce leaf drop during stressful periods of drought, for example. These things are all critical factors to reduce the overall level of disease. Sanitation, obviously, if you catch you see knots in the field, pruning them reduces the inoculum and you move it, moves it away. And then we've always said when people do things by pruning by hand, you could easily disinfect with sodium hypochlorite if you have a pruning shears. But the problem with sodium hypochlorite is that it is very corrosive, and workers don't like to use it. And so we worked on that aspect in some of our research to try to come up with another material. Gall X is registered. You can paint the galls, but if you have a lot of galls, it's a lot of labor. And we're trying to move away from labor. So the best way is to use preventative treatments or protective treatments like copper-based materials to prevent any sort of injury to occur. And copper is still very toxic to the pathogen, and if properly timed, as we'll go over, we can manage the disease with that treatment. So let's just go over some things that we just came up with. This is recently registered just this past year in April. We came up with a new sanitizer. What's it called? It's called quaternary ammonia compounds. This quaternary ammonia compounds are used actually in the mills already. They use to surface sterilize equipment in the mills so that you don't have to worry about bacterial contamination between lots or when leaves are brought in. In between, you can sanitize the equipment and keep bacterial populations very low. This quaternary ammonia compound is used in post-harvest. I do a lot of post-harvest work on tree fruit crops, and they're used to clean all kinds of, not just in the mills, but they're used to kill bacteria on all kinds of handling equipment for fruit crops, including olives. It's basically why we like it so much. It's one of the big characteristics is it works in the presence of organic load, and it's non-corrosive. So these are very important aspects. So we did some basic tests. This is about 2 years ago. We showed that it was very toxic to the bacterium. This is just a little curve that shows the exposure in 35 seconds. We can reduce the populations from 100% down to just 4%, just with a short duration exposure. And we can see that the bacterium is so heavily populated here, and there's just a few cells left in these little short exposure times. So it's very toxic to the pathogen. We look at hard surface. We contaminate it, like the beater bars are made out of PVC, and this PVC piping is used for automated harvesting systems, and some of the grape harvesters that are used for olive. And we've showed that we can smear the bacterium on with macerated olive tissue all over the pipes, and we can treat it with the QOC for the quaternary ammonia compound for 90 seconds, and then we could lightly rinse it with water, and we can see the effects here. Water, get our population counts, 4,000 CFUs, colony forming units. When we use the sodium chloride, we get it down to a reasonable level, about 1,000. But then when we use Stairback Quat, this is the one that they use in the mills, the olive mills, brought it basically down to zero, just a few cells left. And again, a few cells aren't going to cause disease. It takes thousands of cells to cause disease, like I showed earlier. And the product that we were working with is this Decosan 315, and at 2,000 parts per million, it provided very similar to the quaternary ammonia compound used in the olive milling process. So what we did is we moved forward. We showed that it works in the presence of organic matter, and we did some tests here. We contaminated pruning equipment. This is just a hedger. We sprayed the bacterium on there, and then we went and made injuries, like scraping injuries, where we cut branches, where we caused those types of injuries on the branch. And then we, nothing more than just inoculating that blade, and then going to make these cuts. And then again, about 4 months later, we see knots developing, and on the non-sanitized one, we're seeing 20 to 40 knots per branch. And when we used the sodium hypochlorite, we got that down to maybe 5 per branch. And then when we get down to using the Decosan, 0 here. And when we get it used with a follow-up with a corticoid, consuming treatment following that as a mixture, we show we can get the best results. And this is just non-inoculated, showing there's a control in there that we don't get anything if we don't get the bacteria on. So basically what we're showing here is real-world testing of the quaternary ammonias as a disinfectant for equipment, and it's non-corrosive, and it doesn't have odors like the chlorine, so it's very worker safe. So basically what we show is that we've got a nice new material registered. It was approved in through this labeling process, a 24C, a special local need registration. This passed in the state of California. It basically works in the present organic load. It's non-corrosive, and it's called Decosan 321. The parent product is Mayquat, but it is registered for use in California. Field surveys, we're real excited about that real quick. We did surveys in copper sensitivity. We looked at from orchards. We did over 147 strains that we've looked at. We just basically breaking them into categories of what we call the minimum inhibitory concentration of less than 20, greater than 20 to 50, and then greater than 50. And we basically we break them down into these categories. We looked across many different fields in the various orchards that we went into. Total isolates, most are sensitive to copper. That's 95% of the strains we collected are sensitive to copper. But the alarming news here, and I'm not being an alarmist, but there is a potential for resistance. We see a small percentage, 2% being moderately resistant, and 3 of those 147 being about 2% of the total, showing some high levels of tolerance to copper, where they're able to grow in that presence of copper. So the good news is, where we found this copper-resistant strains, they were in these orchards that have been in place, as we just heard from some of the history. They've been in place for 100 years, and they've been using copper over and over again. And so if we use copper only, and we use it indefinitely, we're going to select for resistance. That's basically what that shows us. In new orchards, it seems like we're starting with brand new populations. You're going to be up here with sensitive populations. But what we want to do now is make sure you never get to that. So we want to introduce new modes of action, other materials. Okay, so what are the new bactericides? So the first thing we talk about with bactericides are antibiotics, and that's a bad word in agriculture. You've been all heard about this over the years, that antibiotics can be a big problem. So what we did is we found a loophole. And the loophole in agriculture is that we found an antibiotic that's not used in animal or human medicine. So it's only used in plant agriculture. That's a rare thing. And curcumin is the commercial name. Kasugamycin, just like streptomycin and these other mycins, they're antibiotics. And so this one here is produced in Japan. It was produced and is used worldwide. We actually have import tolerances where we can import commodities from other countries with residues of this material sprayed on vegetable crops like in Mexico, and we have import tolerances. So what basically tells us that this thing has been around a long time. It's very safe because it has a very short half-life. And if we use it only in the winter after harvest, we use it in the winter when there's cold periods, or we use it in the spring when leaf drop is, we could have a 120-day PHI, which is a pre-harvest interval, before we harvest in October. And so what we did, we're doing this through the IR4 program. What we're showing is that the residues for these antibiotics will be zero by the time we get to harvest. So there's no question that we're going to adulterate. We're talking about adulterating our olive oil. They're not going to adulterate it with a pesticide with these kinds of labels and usage labels. So the companies, Arista, and we're working with MicroShield here for New Farm, which is an Australian company. We're registering these products. They're in the IR4 program, and we're working towards getting these things made available so we could use them legally on olives to prevent olive knot from happening. And the good news is that we're not going to have any real issue with these things showing up in our crop. We've been able to register it on pole fruits. It's been registered in the US EPA now, Persumin, and it has been registered, MicroShield, oxytetracycline has been registered on pole fruits since the 1970s. So there are precedents with other agricultural crops where there's registration of these, and we do have these things in process. So in 2014, we started with the IR4 A priority. So that means it got into the system, and the rescue studies are ongoing. And then just this past September 2015, oxytetracycline was accepted. And these are spiral plates, and what people know that I talk about spiral plates, we put on antibiotics at high concentrations and a machine that spins out, and basically you get lower and lower concentration. And then we streak the bacterial populations on here, and each one's an individual strain. But you can see we can do a number of strains, and you can actually see the inhibition zone. And at the higher concentrations of the bacterium, in this example, Pseudomycin, we can inhibit the growth. It shows it's active against the bacterium. And in the control plate, we get continuous growth. There's no antibiotic here. Like most things, we get a standard, what we call a baseline curve of sensitivity. And we're really happy that both the Pseudomycin and the oxytetracycline are all the strains we tested, including the copper-resistant ones that we showed. There's only 2%, and the copper moderate resistant ones are 2%. They're all sensitive to Pseudomycin and oxytetracycline. So that's very good news. So there'll be different modes of action. The oxytetracycline has a unique mode of action. The Pseudomycin has a unique mode of action, and the copper has a unique mode of action. So you can see where I'm going with this. If we can develop a rotational program or programs where we mix these products, the bacterium is much more difficult, finds it much more difficult to select for resistance when you have different modes of action, because there's more chance. Go ahead. Question?
Would the spray timing be the same as what you're trying to accomplish with the copper sprays? I mean,
yeah, they're going to be exactly the same, because we got wound healing working for us. We're going to have, if there's injuries made, we can treat, and we don't need to have long residuals for some of these antibiotics. And if we mix them with copper, we can get longer residual activity if we're going into the winter period. So we're looking at fall after harvest applications. We're looking at winter treatments when there's cold, injury, and rain, like I showed you in some of those graphs. And we're looking for at leaf drop. So it's basically November after harvest to April timing, and it could be anywhere from 2 spray. I think you need 2 minimum, 1 after harvest and 1 at leaf drop, and then additional sprays around cold periods in the winter time. That would be our timing. Question?
Are any of these antibiotics going to be organically acceptable?
The question is any of the antibiotics going to be organically acceptable? Well, oxytetracycline was organically accepted, but it was taken off by the NOSB recently because of pressure from various consumer groups. Persumin, these are all products that are biofermentation products produced by a bacterium known as Streptomyces. And there's different species, and they produce these things, and they were accepted as biological, but because of the fear of resistance in humans, the NOSB, the National Organic Standards Board, was kind of forced to take off oxytetracycline or MicroShield off that list for like apples and pears. But with Persumin, the company's willing to petition the NOSB because is not used in human medicine. It's not used in animal agriculture. So we can petition them to accept cassumin as an organic product because that threat of cross resistance isn't there for for people taking antibiotics for if they're sick. Cassumin is a different mode of action, so there's not really a threat that you're going to have resistance from being exposed to cassumin. Does that make sense? Okay. Let me just quickly wrap up here. We'll see if we can get some. The good news here is these are just some of these efficacy tables. Again, Paul was talking about variation and experimental potential for error. We try to control the rates of error. What we're basically showing here is that statistically, these graphs got a little bit screwed up here, but statistically we're able to show that these things we can control the test with, control the variation and do the statistical test by having enough replications. But basically when you see a letter A and then you have these smaller bars with different B's, what we're basically showing through an analysis of variance, we can show that there's significant differences between the treatments. All these treatments with B's here are basically the same. With the C's, they're different from the B's, but there's some groups are B, C, so they're not different from each other. Pseudomycin by itself is a B here, but when we put pseudomycin with copper in a mixture, we can get a C group, so it shows significant improvement in that. We also looked at copper-resistant strains, and again, looking at the copper not working too well, and then when we use the antibiotics, we're getting good significant reduction. So that's the evidence for no cross-resistance.
Jim, real quick on that, the copper hydroxide versus the oxychloride. I saw you had them both up there, but in terms of efficacy.
That's a tough question. We're asking about different formulations of copper. Copper comes in many different formulations. Hydroxide, there's mixtures of hydroxide with these other combinations of chlorides, and basically we don't really see huge differences in that. I know that's been a big question. We're seeing more of a difference. I'll show you a slide in a minute. More of a difference in the actual total amount of metallic copper equivalent per orchard application or per acre application. That seems to be more critical than the different formulations of the copper. So just quickly here, we did further studies. These are done up in the Yuba City area, Marysville. I guess that's basically District 2 based on the map that we saw as far as the districts are concerned. We did these compared to control. We went out and the grower let us actually inoculate after a commercial harvest. We went in, saw wounds, we inoculated them, and again, 6 months later, there's 60% of the wounds that we inoculated had knots on them. We tested an experimental material, didn't work. We looked at the grower standard. Obviously, he's using 4 pounds Coside 3000 with zinc sulfate and lime. He got a significant reduction. We used our Kenton cassumin and saw the best results there. So the promise there looks very exciting. Persistence. I know I'm running out of time here, but a lot of questions over the years that we've worked on this is how do we make this thing last? And if we put it on at harvest, can we make it last into the December, January period? Again, looking at the high rate, here's the maximum labeled rate of Coside 3000, 7 pounds. Did an excellent job on leaf lateral wounds on the stems and leaf scars. We dropped the rate in half here, and we added various types of materials to try to improve the persistence from lime to tactic, new film, if you're familiar with some of these materials. And you can see there's quite a bit of variation. Most of the materials work well on lateral wounds. We get a significant reduction. Those numbers show all significant reduction compared to the untreated control. The new film, the Omni oil, did the best on leaf scars as far as our testing goes. So we can get improved performance. So you cut your rate of copper in half, you add your surfactant or adjuvant sticker, and you can. These are the products that we would recommend when doing that. And lastly, I just want to point out that we did some work, and I think this has a real impact. We did timing of these applications on injuries, and there is some bad news that if you wait, say this is right after an injury is made, we make these timings of the risperidone or cocoside applied, and here's the control, very high level of disease. These were ratings, scores really 75 to 100% of the inoculation sites have disease. If we just do it on the same day, and this is within 24 hours of the making the wounds, we can get excellent results. If we wait to the next day, 2 days, 3 days, 4 days, 7 days later, we lose efficacy. And so these are again inoculated injuries. So the key message is if you're mechanically harvesting when things are moist, it rained, and you get your harvester's going through in the early morning and it's wet, and he's creating injuries and he's dragging through those knots, and he's basically inoculating your orchard. If you come in with copper right after that, at the proper rates that we just showed you, you can control the disease at a very high level. If you wait a day, I'll do it tomorrow, you're going to be in big trouble. So the key thing is to block off your orchards as you harvest. So the plan, well, we work with a lot of BCAs, and John Post is one of our close people that we're working with. So he immediately interpret the data, we're going to block this off. We're going to harvest for 4 hours, we're going to spray the next 4 hours, those areas that we just treated. So this is a good strategy for protecting it. If you get hail damage in the middle of May, you can get in there the next day, you're going to control the disease, even though it's very localized. You can control the disease. If you wait a week, it's too late. Wait 3 days is too late. I'll stop there. We got a number of highlights here. We know that injuries are involved. We know that inoculum levels are critical. We need lots of knots to get disease. Wounding, the good news is the trees heal up, but we can get systemic infections if we get that cold followed by rain. We got some good news with sanitizing equipment. We have a registration for quaternary ammonia. It's the Deco Sand. It's registered and commercially available. We like this material. It gives us many advantages over the standard sanitizing treatments. It can be used on pruning equipment. It can be used on harvesting equipment. As far as our field applications with chemicals, we're coming along. We think coppers are still very effective for the majority of the industry. We know that adjuvants improve the performance, and we can use lower rates, and we're developing new modes of action with those antibiotics. And then these are the antibiotics, and we expect these to be registered probably by 2018 for pseudomycin, and since it's just done this year, it'll be probably 2020 for oxytetracycline. Question?
The quaternary ammonium compound, that's not registered for organic. Correct.
And this is not treating the plants, it's treating only it's not an organic material, but it's treating the equipment, for sanitizing equipment. And if you rinse that afterward, you're not putting it on the orchard. Okay, applications within 24 hours are critical for managing the disease. And that's how you maintain high efficacy of your treatments. Thank you very much. I know it went a little bit long, but hopefully we learned a little bit about some of our research, and thank you for a little bit extra time for this session.